Good morning, dear students. Next, we can go through a formula regarding the calculation of density, and the formula it is connecting density, this Avogadro number, and also the unit cell dimension, that is A, or the unit cell edge length A. Okay. And also the formula it is like this. The for density the term it is rho. Okay, so density rho is equal to small letter m in n into capital letter M divided by NA into small a the whole cube. Okay, small letter n into capital M divided by NA into a cube, where small letter n it denotes the number of atoms per unit cell. Okay. Small letter n denotes the number of atoms per unit cell. So we have seen the number of atoms per unit cell in the case of a simple primitive lattice, isn't it? In a simple cubic lattice or a simple primitive lattice, n is equal to 1, isn't it? For a simple cubic lattice, and for a body-centered cubic lattice, for BCC, n is equal to 2. Okay, then for an FCC lattice, then n is equal to 4. Okay, so this is the case of the number of atoms for a simple primitive, for a body centered as well as the face centered. So n represents the number of atoms per unit cell. Then capital M. What is capital M? Capital M, it is the molecular mass of that particular crystal or that particular compound. Okay, sorry, M is the molecular mass. Then Na is the Avogadro number, that is 6.023 into 10 raised to 23 Na. Then small letter a, it is the edge length. Small letter a is the edge length of a unit cell. Okay, small letter a. See, suppose this is the unit cell. See, suppose this is the unit cell. This is one unit cell, and also we can see this is the edge length A of that particular unit cell. Okay, so this is the edge length A. Then and also there is a formula connecting this edge length A and volume. See, if we are knowing this, the value of A, volume of that particular unit cell, that is equal to A cube. Okay, volume is equal to A cube, the cube of this, the edge length. So you have to do some problems with this that I will do in our Google Meet session. Okay, so next we can go through the next topic, that is the laws of crystallography. Okay, so I think you are thorough with the formula. Density rho is equal to n into capital M divided by Na into a cube, where small letter n it is the number of atoms per unit cell. M is the molecular mass, Na is the Avogadro number, and A is the edge length. So next is the laws of crystallography. Laws of crystallography. Laws of crystallography. Okay, so mainly you have got 3 laws to study. The first one that is the Steno's law of the constancy of interfacial angle. Okay, Steno's, S-T-E-N-O, Steno's law of the constancy of interfacial angles. Steno's law of the constancy of interfacial angle. Interfacial angle. Then the second one, that is the Hayes law. Hayes, the spelling it is H-A-U-Y''S. Hayes law of rational intercepts. That is the second law. Hayes law of rational intercepts. And the third one, that is the law of constancy of symmetry. Law of constancy of symmetry. So these are the 3 laws regarding the laws of crystallography. The first one, that is the Steno's law. The 3 laws are very important. The first one, that is the Steno's law of the constancy of interfacial angle. Constancy of interfacial angle. Then the second one, that is the Hayes law of rational intercepts, and the third one, that is the law of constancy of symmetry. Okay, so you have to go through one by one, and the first one we can see, that is the Steno's law of the constancy of interfacial angle. Steno's law of constancy of interfacial angle. See here, See, in this Stenos law, see, we can see that, see, suppose a crystal, how a crystal grows. Crystal grows means there will be deposits on the surface of that particular crystal, and again gradually this crystal it will be growing, isn't it? That means one unit cell, we can say it is in the case of a unit cell, that is part by part the crystal it gets accumulated, and gradually the crystal size will be increasing. You have studied in your S2 classes, isn't it, regarding the crystal growth, isn't it? So what happens is that, see, suppose this is the shape of a particular crystal, see, in the shape of a benzene ring. Okay, so this is the this is one angle for that particular crystal. So what happens is that as this crystal grows, what happens, the shape is somewhat similar, the shape will be almost similar, and also the angles between that two faces, that will be the same even if the crystal grows. Okay, while during the growth of the crystal, the angle between the two faces it will be the same whether it grows or not. Okay, so if it reaches a much bigger sizes, then also the corresponding angles, okay, not this one and this one, not this one angle and this angle, it should be the corresponding angles. Okay, so this angle and this angle it will be the same even if the crystal is growing. Okay, so that is the Stenos law of the constancy of interfacial angle. So this law states that the angles between the corresponding faces, okay, the angles between the corresponding faces, the angles between the corresponding faces on various crystals, angles between the corresponding faces on various crystals of the same substance are constant. Of the same substance are constant. Okay, so this is the law, Stenos law of constancy of interfacial angle. That means the interfacial angles of a particular crystal for the same substance. Suppose, for example, if it is sodium chloride crystal, both are sodium chloride, and if the crystal is growing, see, the angle between the corresponding faces it will be the same for both the cases whether the crystal grows or not. Okay, so that is a simple law regarding this interfacial angle. And also then the second one, that is the Hayes law. Okay, second law, that is the Hayes law, Hayes', Hayes law. So here this Hayes law means it is used to establish the law of rational intercepts. It is the law of rational intercepts or rational indices. Okay, it can be stated in both ways. It is the law of rational intercepts, or it is the law of rational indices. Okay, so here this law of rational indices, see, suppose this is normally these crystals it will be represented by using three axes. Okay, the x-axis, the y-axis and the z-axis. Okay, so these are the three axes. Let it be x, then y, then z. So this normally this crystals they are represented by three axes, and these three axes they are called as the crystallographic axis. Okay, so these three x, y and z axis they are called as the crystallographic axis. X, y and z. Then suppose here, suppose these are this is the origin of this particular, or the center of this particular crystal. Not the center, it will be the origin, or it will be the corner, that is this particular point. Okay, so this is one corner, and this point we can denote it by O. Okay, so O. So this is O, then this is one edge length, that is this is one axis, or it can be one axis, OX axis, and this is the OY axis, and this is the OZ axis. Okay, OX, OY and OZ. Okay, that is what I am representing here. Okay, OX, OY and OZ axis, the three crystallographic axes. And let consider we can draw three unit intercepts. Suppose these are the three unit intercepts that is cutting these three axes. Okay, let it be capital letter A, then B and then C. Okay, so these three are the three unit intercepts which cut this particular axis. Okay, so we can join these three, A, B and C, we can join like this. And also let this distance, let OA, let it be A. Okay, let the edge length of this particular unit cell, let it be A. And let OB, let it be small letter B. And let OC be small letter C. Okay, so we got 3 edge lengths, isn't it? That is A, B and C for that particular unit cell. That is, while we are looking in this cube, see, this is the point O, this is OA, and this is OB, and this is OC. Okay, so this 2 points, okay, so this edge length of this particular unit cell, let it be A, this one let it be B, and this one let it be C. Okay, so this is C, this is A, and this is B. Okay, so this is the point O. That is what I am representing here in this paper. Okay, so these are the 3 unit intercepts A, B and C. That means these 3 unit intercepts will be cutting the plane at A, B and C. Okay, and also see, according to this law, according to this Hayes law, the intercept of any face, see, suppose I am cutting these 3 planes with another 3 points, okay, another 3 intercepts, okay, cutting these planes with another 3 points or another 3 intercepts. Then again we can draw a triangle like this, and let this triangle, let it be K, L and M. Okay, K, this point K, and this point L, and this point M. Okay, so according to this law of rational indices, it states that the intercepts of any face of a crystal, see, this is one intercept, isn't it? OA is one intercept and OL, it is another intercept, isn't it? So the intercepts of any face of a crystal along the crystallographic axis are either equal to the unit intercepts A. Okay, that means this OA distance, OA, let it be A, the distance let it be A, and again AL, it can be A or it can be the whole number multiples of A. That means if this distance, that is AL, it can be 2A, 3A, 4A, like that it will be. Okay, so this distance, the intercepts of any face of a crystal along the particular crystallographic axis are either equal to the unit intercept A or simple whole number multiples of this A. Okay, so that is the law of rational indices. So I am writing the law that this law states that the intercepts of any face of a crystal, the intercepts of any face of a crystal along the crystallographic axis, are either equal to unit intercepts A, B or C or simple whole number multiples of the, okay, or simple whole number multiples of the. Okay, so this is the Hayes law of rational intercepts or rational indices. See, if we are taking this cube, see, this edge length, this is A, okay, this edge length, it is A, isn't it? Then again this distance, this is a simple cube, isn't it? So this distance again, it is A. So the total distance, if this is OA and this is OK, we can say that the total edge length up to this point, it will be 2A, isn't it? So we can say that according to this law, the intercepts, that means the intercepts of any face of a crystal along the particular crystallographic axis are either equal to the unit intercepts or it will be the simple whole number multiples of them. So here it will be A, here it comes 2A, here it comes 3A, isn't it? So that is a whole number multiple of that particular axis. Okay. So likewise we can write here also. So this is the diagram you have to draw if this Hayes law is asked. So this OX, OY and OZ are the 3 crystallographic axes. OX, OY and OZ are the 3 crystallographic axes, and ABC, let it be a unit plane. Okay, so the intercepts will be small a, small b and small c. That means this particular distance, that is OA equal to A, then OB equal to B, and OC equal to C. Okay. So according to this law, the intercept of any face, that means again the next intercept, that is at K, L and M. Okay, the intercept of any face on the same three axes, isn't it? The same axes are there. On the same three axes will be the simple whole number multiples of A, B and C. So we can write here it as the axis here it will be, let it be 2A, it means double, isn't it? 2A, then 2B, then 2C. Okay, like that we can write if it is a simple whole number multiple. Okay, so that is the law of rational indices, and it is very important, this law of rational indices. Okay, hope you are clear with this Hayes law. And the next one, that is the law of symmetry. The third one, that is the law of symmetry. Law of symmetry that we have seen already. That is, what are the symmetrical planes, or how a crystal can be divided with respect to, there will be a plane of symmetry, isn't it? A plane of symmetry might be there, then an axis of symmetry might be there, axis or axis will be there, isn't it? Axis of symmetry will be there, and also there will be a center of symmetry for a crystal. Okay, so the definitions for these three that we had already discussed. So the definition of these three, that is the plane of symmetry, axis of symmetry and the center of symmetry, it gives the laws of symmetry. You have to go through the definitions for these three, that gives the law of symmetry. So that means a crystal will be having a plane of symmetry, if when it is cut into two equal halves by a plane, isn't it? And one is the exact mirror image of the other, that gives the plane of symmetry. Likewise, you know this axis of symmetry as well as the center of symmetry. We have discussed in detail in our previous session, isn't it? Okay. Then the next we can go through Weiss indices and Miller indices, and this is also very important, the Weiss indices and Miller indices. Then the next one, that is the Weiss indices. W-E-I-S-S, not apostrophe, Weiss indices. Okay, Weiss indices. So again, I am drawing this diagram. Then the center, let it be O. Then X, Y and Z. Okay, X, Y and Z, and again unit intercepts A, B and C. These are the unit intercepts which cuts the three crystallographic axes A, B, C. And again there will be another intercepts at the points K, L and M. Okay, again this will be cutting at K, L, M. Again we can draw like this, K, L, M. So according to the Hayes law of indices, we can say that this is a unit cell A, B and C. Okay, the edge length, let it be A, B and C. Suppose these intercepts, that is OL, then OM and OK, these will be having a distances at 2A, 4B and 3C. Okay, that is the distances of OL, OM and OK. Okay, let it cuts the intercepts at the distance 2A, 4B and 3C. Okay. So here the coefficients of this A, B and C. What are the coefficients of A, B and C? That is 2, then 4, then 3, isn't it? So this coefficients of A, B and C, they are called as the Weiss indices. Okay. So Weiss indices means it is the coefficients of A, B and C. That means here it will be equal to 2, 4, 3. So that gives the Weiss indices. It is very simple. And also, so here in this way we can represent any crystal in terms of the Weiss indices. Just you have to write the coefficients of A, B and C. A, B, C be the unit cell dimensions or the unit cell edge lengths, isn't it? So Weiss indices means it is the coefficients of A, B and C. That gives the Weiss indices. Okay, suppose see for example a crystal, it is having the intercepts, or it will be cutting the three crystallographic axes at the distance 4A, then 3B and 5C. Okay, So what are the Weiss indices here? Weiss indices means it is the coefficients of A, B and C. So here the Weiss indices will be 4, 3 and 5. This is just an example. Okay. So this is the Weiss indices. This is how we are representing the Weiss indices, and normally, but this is not used. This Weiss indices is not used. Instead of Weiss indices, we are using Miller indices. Okay. Miller indices, it is very, very important. Miller indices, it will be asked for sure, and also you have to calculate the Miller indices of a particular plane. Okay. So by using this Miller indices, what is the purpose of this Miller indices? It is used for representing a crystal. Okay, with the help of Miller indices, we can represent a crystal. So Miller indices are used for representing a crystal. It represents a crystal. And also, see, this Miller indices means it has got a set of integers. Miller indices has got a set of integers, and the integers we can denote it by the letters H, K and L. Okay, H, K and L. So these are the set of integers. So Miller indices, it is represented by a set of integers H, K, L, and is used to describe a given plane in a crystal. This HKL represents a given plane in a crystal. Okay, so for a crystal to be represented, we are using these three integers H, K and L. Okay, and also now you have to go through how this Miller indices are calculated. Okay, so here, so Miller indices, we can write the definition as it is a set of integers HKL which are used to describe a given plane in a crystal, and also it is proportional to the intercepts of that face. Okay, it will be proportional to the intercepts of the face. That means it will be a whole number multiples. Then again, see how to calculate a Miller index. Okay, so normally for a phase KLM, we have seen a phase KLM, isn't it? KLM. Okay, see, for a phase KLM, the unit cell dimensions, let it be A, B and C. And again, we have seen a Weiss index that is 2A, then 4B and 3C, isn't it? Weiss indices for the plane 2A, 4B and 3C. What is the Weiss index for this plane? That is 2, 4 and 3, isn't it? So this is the Weiss index. Then from this Weiss index, you have to calculate the Miller index. Okay, so for calculating the Miller indices, first of all you have to take the reciprocal of these three integers. Okay, so reciprocal of 2, 4, 3 means it will be 1 by 2, 1 by 4 and 1 by 3. So first step, you have to calculate the Weiss index, and the second step, you have to take the reciprocals. Okay, second step, you have to take the reciprocals, that is 1 by 2, 1 by 4 and 1 by 3. And the third step, you have to take the LCM. Okay, you have to, here the LCM, it will be 12. Okay, so you have to multiply each term with the LCM. So 1 by 2 into 12 then is to 1 by 4 into 12 is to 1 by 3 into 12. You have to multiply it with the LCM, or multiplying it with 12. So here it will be 6, then here it comes 3, here it comes 4, isn't it? So 6, 3, 4, 6 is to 3 is to 4 is the ratio we obtained. And also we can say that the plane, the Miller index of that particular plane, that is 6, that is a 6, 3, 4 plane. The Miller indices, it is a 6, 3, 4 plane. Okay. Hope you got to calculate this Miller indices. That is, the Miller indices means it is a set of integers with HKL notation. And the first one, you have to calculate the Weiss indices for a particular plane. And in step 2, you have to take the reciprocals. And in step 3, you just take the LCM and multiply with that LCM. Okay, then you will be getting the Miller indices of that particular plane. So here 6, 3, 4 is the Miller indices. And H is equal to, here H will be equal to 6. K will be equal to 3 and L will be equal to 4. Okay, so that is how you have to calculate the Miller indices. Then another example, see another plane, that is example 2, another plane with infinity A is to 2B is to C. Okay, infinity A 2B is to C. So here first step you have to calculate the Weiss indices. Weiss indices means the coefficients of A, B and C. So here it will be infinity, then 2, then 1. Okay. So this is the Weiss indices for that particular plane. Then what is the next step? You have to take the reciprocal. So reciprocal means it will be equal to 1 by infinity, then 1 by 2, then 1 by 1. Okay. So that will be 1 by infinity is to 1 by 2 is to 1. Then what is the next step? You have to take the LCM or multiplying by 2. Okay. So multiplying by 2, here the LCM it will be 2, isn't it? So here it will be 1 by infinity into 2. Again 1 by 2 into 2 is to 1 into 2. So here it will be equal to 1 by infinity is 0 into 2. Again 0 is to, here it will be 1. Then here it will be 2. Okay. 0, 1, 2. So we got the Miller indices as 0, 1, 2. Sorry, 0, 1, 2. So this is a 0, 1, 2 plane, or the Miller indices of that particular plane will be 0, 1, 2. So the Miller indices for that particular plane will be 0, 1, 2. So here H is equal to 0, then K is equal to 1 and L is equal to 2. Okay. So the Miller indices for that particular plane will be 0, 1, 2. So we can represent it by a bracket and also should not put comma in between. Okay. 0, 1, 2 plane. Then again, we have to go through some of the examples given in your textbook also. See, for example, another example, 2A, 3B and C, another plane. Okay, example 3, 2A, 3B and C. So here for 2A, 3B and C, what is the Weiss indices? That is equal to 2, 3, 1, isn't it? That is the Weiss index. Then taking reciprocals, it will be 1 by 2, 1 by 3 and 1. Then multiplying by the LCM, that is multiplying by 6, it will be 1 by 2 into 6 is to 1 by 3 into 6 is to 1 into 6. Okay, so here it will be 3 is to 2 is to 6. So the Miller indices will be 3, 2, 6. And the plane is called as a 3. Miller indices will be 3, 2, 6 and the plane it is called as a 3, 2, 6 plane. Okay. So this is how you have to calculate the Miller indices. Okay. Then another example. This is very simple to calculate, but it will be asked usually, very important question, and also it will be asked usually for a 4-mark question. Sometimes you are asked to calculate this Miller indices also. Okay. So then another plane, that is 2A, example 4. Another question which is given in your textbook, that is 2A, minus 3B, minus 3C. Okay. So the Weiss indices will be 2 minus 3, then minus 3. Okay. 2 minus 3 minus 3. Then you have to take the reciprocal, that is 1 by 2 minus 1 by 3, minus 1 by 3. Then you have to take the LCM. So multiplying by 6, we will be having 1 by 2 into 6, then minus 1 by 3 into 6, again minus 1 by 3 into 6. So here it will become 3 is to minus 2 is to minus 2. Okay. So the Miller indices are, we have to write like this, 3. Then for minus 2 you have to written as bar, you have to write it as bar 2. Here also you have to write it as bar 2. So the Miller indices are 3, bar 2, bar 2 and the plane it is called as a 3, bar 2 plane. Okay. So hope you got the point, or you got the how to do the Miller indices. Okay. So next we can go through some of the problems here that we will be seeing in our Google Meet session. Okay. Thank you, and you have to take care of this Miller indices also. It is very, very important. Thank you.